Hello and thanks very much to the LEAF organizers. My name is Stefan Kadocki and I'm an assistant professor of pathology and lab medicine at the Children's Hospital of Philadelphia, where I do clinical work in the divisions of transfusion medicine and pathology informatics. And today, my talk is titled A Concise and Engaging Introductory Data Skills Curriculum for Healthcare Professionals Using R. And this is really something that I'm very excited to talk about in this forum because it's the result of a wonderful collaboration with a number of colleagues that started when I was a resident, and I felt that there was a painful lack of practical data literacy in data skills education and medical curricula. And out of this vision was born that all healthcare professionals, not only informaticists, but also pathologists, internists, medical students, lab techs, nurses, and clinical research coordinators, all of them could and should learn basic data skills. And ideally with a modern framework that streamlines collaborating with data professionals like biostatisticians and data scientists. So first of all, I want to acknowledge my colleagues Joe Rudolph, Patrick Mathias, Dan Herman, and Amram Obstfeld, all of who are accomplished pathology informaticists who shared this vision and who also helped me put together this presentation. I have no disclosures. And after participating in this session, you should be able to define data literacy and discuss the data literacy gap in medical education. You should be able to define the term computational document and cite some benefits of using a computational document as a framework for teaching data analysis skills. And finally, you should be able to cite some teaching strategies that you can employ to improve a novice programming curriculum. Let's start by defining what data literacy skills are. And this definition, from what I can tell, is the most widely cited one by D'Ignazio and Bargava. And it comprises 4 domains, the first of which is reading data. And this rubric includes to really be able to understand and interpret data that is presented to you as graphs or tables with statistical summaries. So that's reading data. Then there's working with data. And this includes being able to acquire data in various formats, not just Excel, and from various sources, not just from a file on your computer. And also understanding the kinds of problems that can occur during data entry, data cleaning, and validating, and how to mitigate them. So having a sense of what the best practices are for working with data, and also collaborating with others. Maybe emailing Excel sheets is not always the best option, although in some cases it very well may be. Then there is analyzing data. And here we're talking about taking raw data and creating artifacts such as tables and graphs that can be read and interpreted by others. This also includes statistical modeling, all the way from doing a t-test to building a deep neural network. And I'm not saying that you need to be able to build a neural network to be data literate, but you should be able to figure out which statistical test to do to answer a specific question. And sometimes that statistical test may turn out to be machine learning or neural network. And finally, there's the rubric of arguing with data. And this is the art of effectively communicating the message that is based on data, either verbally or by creating reports that can tell a compelling story. So these all seem very useful skills to have in the practice of medicine. So the question becomes, why don't we learn this stuff in medical school? Why is there a data skills gap in medicine? And much of the points on the slide are taken from a really great presentation by my friend and colleague, Peter Higgins, from the University of Michigan, titled Tidy Spreadsheets in Medical Research. And I put the YouTube link here on my slide, and in the YouTube recording of this presentation, I will link to this talk. So data skills are de-emphasized in undergraduate and graduate medical curricula. By the time you're expected to do clinical work, you've got no time, so it's difficult to catch up at the same time as fulfilling professional obligations. Probably this has something to do with how deeply ingrained in healthcare culture the Microsoft Excel is. And Excel was created to help small businesses do financial reports and inventory and such things. And as such, it builds itself as an all-in-one solution for entering, storing, visualizing, and making calculations with data, but it is not actually great for any of those tasks. In addition, Excel lacks features to collaborate effectively with others, or to work with data that change, data that are large, and data that are sensitive. Now, more troubling even, Excel hides problems. Excel hides problems in calculations and even causes errors by way of well-intentioned but ultimately deleterious autocorrections. And because Excel mashes together the distinct concerns of data entry, data storage, and data analysis, it really encourages some pretty poor habits, which can lead to really serious problems. And what you do in your Excel sheet isn't recorded anywhere. And part of the reason we have a reproducibility crisis in medicine is because we like to use Excel for our work. Before I talk more about how we try to build a course to address this, I want to highlight some outcomes of this effort. So the course has been taught at multiple venues and has to more than 300 learners and has consistently been very highly rated. And here are some, and here on the left, on the right, I have some projects that course alumni embarked on after taking the course, some of which have led to platform presentations and peer-reviewed publications. Next, I'd like to introduce and contrast three terms that all sound like R. The first is R. And R is a programming language for data analysis. There are lots of things that make R great for clinical data. You can download it for free, it's great for wrangling data, and you can produce publication quality visualizations with it. Also, you can use R to pull data from any of the sorts of databases that are used in most hospital systems. And doing basic data analysis with R is actually not that difficult to learn, even if you're not a programmer and have never written a single line of code. And what really helps here, and is worth highlighting, is that there is a large and welcoming community of people who use R, including in healthcare. And at CHOP, we have an active R user group of 300 or so members from all departments of the enterprise. And these kinds of user groups are popping up in other healthcare systems as well. Then there's R Markdown. R Markdown is a computational document format. So what do I mean by computational document? A computational document is a document that has executable code. And in R Markdown, that code is usually written in R. And I say usually because it's actually possible to write code in Python or other languages inside of an R Markdown document, if that's what you want to do. And after this slide, I'll show you a quick demo of what an R Markdown document looks like. And finally, there's RStudio. RStudio is the name of a company and also the name of a piece of software that this company makes and makes available for free. You can think of RStudio as a fancy editor for writing R and R Markdown computational document. And the technical term is that it's an integrated development environment, but you can think of it as a fancy editor. You can run RStudio on Macs or Windows computers, or if you're concerned about protecting patient data or intellectual property, it's possible to lock down an RStudio server behind your hospital firewall. So let's do a quick demo to see how RStudio, R, and R Markdown relate. This is what the RStudio software looks like when you open it on your computer. You can see three panels. On the left, there's the console. This is where you can write R code and it gets run immediately. For example, I can use R as a fancy calculator and ask it what 2 times 5 is. On the bottom right, you can see the Files pane. And this shows the files that are in your working directory. And on the top right, you can see the Environment pane. This is where R lists the datasets that are loaded into R's memory. And right now, there aren't any datasets loaded, so it says environment is empty. So let's create an R Markdown document. And to do that, I can click on the New Document icon on the top left and select R Markdown from the menu. It'll ask me to provide a title, and I'll name my R Markdown document AMIA and click OK. So now a new pane opened up on the top left right here. And this is the code editor window. And it comes with some demo code written in R Markdown. So we're looking at an R Markdown source document here. Remember that I said that R Markdown is a computational document. And a computational document is a document that contains executable code. You can see chunks of executable code because it's highlighted with a gray background. So here is some R code, summary of cars. There's also some text in this, and there's also some text like this paragraph here. Note that this text contains marks. For example, the two hashtags before the word R Markdown. Here, tell R Markdown that this is supposed to be a header. So R Markdown knows that it should make that text a larger font and bold-faced. One key idea is that you will want to render your R Markdown into a target document, and that's called knitting. I can knit the document to HTML like this. It'll ask me to save the file. I'm just call it test, and I already have a test file, so I'll replace it here. So now we're looking at the rendered R Markdown document rendered to HTML. You can see that the R Markdown text here was rendered as a header. Also, you can see the code that was in the code chunk. As part of the knitting process, R Markdown ran that code, and it's now showing the results here. So from this, I hope you can imagine how you can easily create repeated, reproducible reports that can take in new data or new logic, and you can re-knit the document and get fresh results. So how does R Markdown fit into teaching data skills? To answer this, let's look at the life cycle of a data analysis, and what I'm proposing here is a slight modification of Hadley Wickham and Garrett Goldman's model from their famous R for Data Science book. So you would start by defining the objectives of the project and identify what data you need to meet these goals. Then you import the data into R's memory. Then you tidy the data, by which I mean data cleaning and data quality control. And usually the next step will be to transform the data in some way so you can perform visualization and modeling, which are the main engines of knowledge generation. In a typical data analysis, transforming, visualizing, and modeling happens not only once, but over and over. This is called the understand cycle and highlights the iterative nature of data analysis. The final critical piece is communication of the insights in such a way that they can eventually get turned into action. And that can be through a publication or a report or some other way so that the analysis can be used for decision making. So in reality, as you're working on the project, this workflow flows in both directions, and you may need to go back to a previous stage. But when you rerun the analysis, this is the order of the steps, and this is how the workflow or how the data flows. We use R Markdown as a substrate for reproducible data analysis workflows that let you gradually build the logic of the data analysis and allow you to add new data at any point of the project lifecycle. Since R Markdown is so central to how we do our data analysis workflows, we don't only teach how to use it, we actually use it to teach data analysis. And we're not the only ones who do this. Blanca Himes does the same thing in her data science course, and I really think we can adopt this for teaching healthcare professionals. So here are some considerations for how we can optimize the learning experience for healthcare professionals who are complete novices when it comes to programmatic data analysis. And the idea here is that the workshop is a great format for this. We want the curriculum to be concise. Everyone's busy and also skeptical that this will actually be useful for them to learn, and many are anxious that they don't know enough. So our entire data analysis course can be run in anywhere between 3.5 to 8 hours over 1 to 2 days. This forces us to be extremely selective for the concepts we want to cover. So we focus on key mental models, leaving out details and referring to an opinionated set of recommended resources. Because we're doing a 1 to 2 day thing, this also really requires comparatively few resources from instructors and learners. Another neat feature of the workshop format is that learners graduate after 1 to 2 intensive days of sessions, which is long enough to give them a sense of accomplishment, but also short enough to leave them energized and hungry for more. In the last few slides, I want to introduce a couple of guiding principles that we've employed and that I think are very useful to consider when you're teaching adult learners, especially if they are anxious, time-starved, and skeptical. The first of these concerns cognitive load theory, and I'm only going to give you a very rough overview of this. But in cognitive load theory, a key idea is that cognitive load is the total mental effort required to learn new material, and it's composed of different types of load. If cognitive load exceeds available cognitive resources, no learning takes place. So the name of the game is to optimize cognitive load, and a good way to do this is by looking at 3 different types of load. The first is called intrinsic load. This is the effort that is actually needed to process the new information. And for novice programmers, that intrinsic load of the content of a programming course is usually extremely high. And you can avoid having your students falling off a cliff by simplifying material and breaking it into smaller pieces. So you want to simplify. The next is extraneous load. This is the work you make learners do by making them have to filter out unnecessary audiovisual content that is not part of the main message. And this is unclear text and inconsistent design language, also verbally expressing an idea in words that are different than what's written on the slide. Look at the slide, and you'll see I created extraneous load in this bullet point in a couple of different ways. My spoken script was different from what's on the slide, and the font is different from the other bullet points for no reason. So I made the design language inconsistent, leaving you to ask yourself why the heck I did that. And that adds to your cognitive load of getting the message. You will want to reduce extraneous load, especially when you discuss challenging concepts such as coding concepts. The last type of load is called germane, and this is the effort spent on connecting new information with existing knowledge that your learners have. And basically, this means that you'll want to think about what knowledge your learners already have as you design your materials, and also because that'll allow you to explain things to your learners in terms that they already know. And that makes it easier for them to move new ideas into long-term memory. Another guiding principle I want to introduce here is the idea of active learning and the difference between passive and active learning techniques. So in passive learning, the learner consumes content without being forced to engage with it. And so this includes things like reading about something, watching a video, attending a lecture, or hearing something explained. So you don't have to actively engage with the material. In contrast, in active learning, you structure the content in such a way that the learner is made to try things out, to do exercises, to discuss a topic, or to try to explain something. And what I'm showing on the right is a figure from a meta-analysis of 225 studies that looked at failure rates for undergraduate STEM courses under traditional passive lecturing versus active learning. And the upshot here is that you have a lot fewer students fail classes when you employ active learning techniques. So how can we implement cognitive load management and active learning into the workshop? To optimize cognitive load, We take great pains to teach only the content that is necessary to perform the initial steps of the data analysis lifecycle, while maintaining a consistent design language, connecting mental models to things, and connecting mental models to things our learners already know. We use animated PowerPoint slides, and we provide, when feasible, printed course materials with key mental models on which learners can take notes. And after about 10 to 20 minutes of introducing new content, we then do your turns. And these are practical exercises, and usually they involve coding. And the coding happens inside of an R Markdown document. This way, learners become familiar with the workflow that they're most likely going to encounter in their actual work with a data professional. The your turns are strictly time-bound, and after each coding exercise, we will immediately go back and live code the solution in front of the class. So this allows us not only to consolidate the material, but also highlight features of the editor interface and introduce useful techniques such as tab completion and looking up documentation, looking up help. So very briefly, since we're running short on time, I want to talk about scaffolded coding exercises. And scaffolded coding exercises are sort of a fill-in-the-blank exercise for coding. For example, here is the command to create a histogram of COVID data that we use in the course with ggplot in R. So this command has a lot of pieces, and all of which are probably new to the learner. So instead of asking our learner to remember all of these pieces to create a basic plot, we provide some scaffolding, which is shown here in black, and we ask the learner to fill in the blanks. And this is very powerful because it allows you as the instructor to gain fine control over exactly what you want to get across at this time. And it also improves the learner's experience because they won't have less frustration with mistyped code, which is not part of what you're currently trying to get across. So one final thought I wanted to leave you with is just how incredibly useful it is to understand R Markdown when you're learning data analysis. And this is because you can render R Markdown into a lot of target formats, not only HTML, which I've shown in the demo, but also PDF, so you can create PDF reports that are good for printing and emailing out. You can also make Microsoft Word documents and even PowerPoint slides. And you can even make interactive dashboards. You can render an R Markdown document into an interactive dashboard. And in my informatics group, we routinely use R Markdown-based dashboards to support clinical operations. So to recap, data literacy skills include reading, working with, analyzing, and arguing with data. And these skills are increasingly needed in clinical practice, but are neglected in medical curricula. Computational documents are documents that contain executable computer code, and they are the substrate for reproducible collaborative data analysis workflow, which is the workflow of modern data professionals. The workshop is a useful format for introducing data analysis skills to novices. Strategies that should be employed in a data analysis workshop include reducing extrinsic cognitive load, active learning techniques, and scaffolded coding exercises. R Markdown as a framework for teaching data analysis exemplifies reproducibility, facilitates active learning, and can be directly used to create clinical data products such as reports and dashboards.